Long before leather enters a factory, it begins here on open prairie. The American bison evolved for survival in extreme environments, freezing winters, intense heat, and constant abrasion from wind, dust, and terrain. These conditions shaped one of the thickest and toughest natural hides in the animal world, a hide that demands a completely different approach than ordinary cow leather. A bison's hide is not uniform, it is thickest around the shoulders and hump, sometimes over twice the thickness of cowhide. This density gives bison leather its legendary durability, but it also creates a challenge uneven fiber structure that must be carefully balanced during processing. At a microscopic level, bison hide is built from densely packed collagen fibers. These fibers evolve to resist tearing and impact, but in leather production, that strength must be controlled. If processed incorrectly, the hide becomes stiff, cracked, or uneven. The entire factory process exists to guide these fibers into flexibility without destroying their strength. In modern leather production, bison hide is never the primary product. It is a byproduct of regulated meat processing, ensuring that no part of the animal is wasted. This makes leather not only a material of strength but one of resource efficiency, transforming what would otherwise be discarded into a long lasting product. Fresh bison hide begins to degrade almost immediately. Bacteria naturally present in skin tissue can destroy collagen fibers within hours. This is why preservation is not optional. It is the first critical decision that determines whether the hide becomes luxury leather or industrial waste. Salt draws moisture out of the hide, creating an environment where bacteria cannot survive. This process halts decomposition without chemically altering the collagen structure, preserving the hide exactly as nature built it. Timing, sword grain size, and coverage density all matter at this stage. Once preserved, hides are bundled and transported under controlled conditions. Temperature, humidity, and transit time are monitored because every hour outside specification affects final leather quality. The journey from animal to material has begun, but the most complex transformation is still ahead. In the next stage, science takes over. The hide will be rehydrated, cleaned, and prepared for chemical transformation, a process refined over centuries but executed today with industrial precision. When preserved bison hides arrive at the tannery, they are biologically dormant. Salt has stopped decay, but it has also locked the hide in a rigid, inactive state. Before any chemistry can occur, the hide must be returned as closely as possible to its original living condition. Every hide is inspected before soaking begins. Bison hides vary widely in thickness, scar density, and fiber tightness. This inspection determines soak duration, water chemistry, and mechanical intensity, decisions that prevent irreversible fiber damage later. Water is not added aggressively, it is introduced gradually, allowing collagen fibers to absorb moisture evenly. Rapid rehydration would cause fiber swelling, leading to looseness and weak grain, defects that cannot be corrected later. Large rotating drums ensure constant movement. This motion prevents fiber clumping and guarantees that thick shoulder areas and thinner flank sections rehydrate at the same rate, a critical challenge unique to bison hide. Soaking removes more than salt. Blood, proteins, dirt, and environmental debris must be completely eliminated. If left behind, these contaminants interfere with tanning agents, causing uneven penetration and long term leather failure. After soaking, mechanical fleshing removes fat and connective tissue still attached to the hide. These organic remnants block chemical access to collagen fibers. Precision is vital. Too much pressure damages the hide, too little leaves contamination behind. At this stage, the hide is clean, flexible, and biologically active once again, but it is still perishable. Without immediate chemical stabilization, bacteria would return, undoing every step completed so far. The next step will permanently change the hide at a molecular level. Through chemistry, collagen will be stabilized, strengthened, and prepared for transformation into leather, a process known as tanning. Untanned skin is biologically unstable. Collagen fibers naturally attract bacteria and moisture, causing decay. Tanning permanently alters these fibers, making them resistant to heat, water, and microbial attack, transforming skin into leather that can last decades. Bison hide presents a unique problem. Its thickness varies dramatically from shoulder to flank, making uniform chemical penetration difficult. Without careful control, the outer layers would tan while the core remains biologically active, a hidden defect that leads to future failure. The first chemical stage is pickling. Acids and salts lower the pH of the hide, opening collagen fiber structures. This controlled swelling creates microscopic pathways, allowing tanning agents to penetrate deep into the hide's core. pH control is critical. If acidity drops too quickly, fibers become brittle. If too slow, tanning agents fail to bond properly. Every adjustment is calculated to match the bison hide's density and thickness. Tanning agents chemically bond to collagen molecules. These bonds prevent fibers from collapsing when wet or shrinking under heat. Once formed, this molecular network defines the leather's strength, elasticity, and longevity. Continuous rotation ensures even exposure. For bison hide, extended tanning times are required to reach the densest shoulder regions. This patience separates luxury leather from mass produced material. After tanning, the hide is no longer skin, it is leather, chemically stabilized, flexible, and resistant to decay. But strength alone is not enough. Luxury leather must also be soft, even, and visually refined. In the next stage, mechanical and chemical finishing will shape the leather's final character, its softness, thickness, and surface appearance. Even after tanning, bison leather is naturally uneven. Shoulder sections can be nearly twice as thick as flank areas. For luxury applications, this variability must be engineered into consistency without destroying fiber integrity. The splitting machine separates the hide into layers using a precision calibrated blade. This allows